So this talk is mostly based on joint works with Iridi Noor, Subash Kot, Gain Kindler, and Muli Safra, but towards the end I'll mention some other works. So let's begin with the basics, with the notion of NP-Hardness that we all know and love. So we're given a SAT formula, a free SAT formula, and we wish to decide whether there is a Boolean assignment that satisfies it. And despite much effort, we don't know any efficient algorithm to do this task. And in fact, we suspect that this is hard. And this is captured by the Cook-Levin theorem that asserts that this seemingly innocent problem actually captures the hardness of an entire computational class of the class NP. And once you have this result, you can start proving that other things are also hard using the notion of reductions. And by now we have a pretty good understanding of the picture. But this is really only a very simple question. So you can ask for a more refined question. So many times, if I find an assignment that satisfies almost all of the clauses, maybe not all of them, then this is sometimes as good as finding a satisfying assignment. So can we do that? Can we solve SAT approximately? Well, the answer is no, and this is one formulation of the PCP theorem. It has many formulations, but here is one of them. So it states that there exists some constant C less than 1, such that if I give you a SAT formula and I promise to you that it's satisfiable, you are not even able to find an assignment that satisfies C fraction of the clauses. And just like in the Cook-Levin theorem, once you have established hardness for some approximation problem, you can start doing gap reductions to prove hardness of approximation results for other problems. But these reductions are a bit more challenging because you need to keep a ratio between the yes case and the no case. But still we have many results, and here are a few examples. So for 3SAT, we know the exact answer. We know that you can approximate within factor 7/8, but you cannot do anything better. We have some results for max cut, click, vertex cover, and set cover, and actually many more problems. But I'd like to sort of focus on this click result. So this result says that you cannot approximate click significantly better than factor 1/n. And 1/n is trivial, it's just one vertex. So let's see this result. So this is the result of Hastad, and he proved the following thing. He showed that given a graph G, it's NPR to tell whether this graph contains a click of size n to the 0.999, or it contains no click of size even n to the 0.001. Sometimes it's easier, but this is the equivalent formulation to think about the promise problem, especially if you try to design algorithms. So you think about it in the following way. You are given a graph G, promised to contain a large click. A click as in the size in the yes case. And all that you want to convince yourself is that you can find the click of size n to 0.001. You only want to convince yourself that you are not actually in the no case. And Hastad showed that this is hard. And again, this is two equivalent formulations of the same result. But note that this theorem, while it's great, it has one annoying drawback. Both in the yes case and in the no case, the size of the click is actually vanishing when compared to the number of vertices in the graph. So here is a natural question. Can we get some hardness result which is similar to that, but when the promise is to have a click of a positive fraction, some epsilon fraction of the vertices? So let's try to shoot for the best thing we can. So let's say we are promised to contain a clique of size 50% of the vertices. So what can we do then? So 50% is a lot, right? So let's try to get at least a quarter. But we don't know how to do that, so let's try a little best. It's still not clear. So can you find anything non-vanishing, and can you find epsilon n for any epsilon constant greater than 0? And the answer is probably not. But we don't know how to prove that. We don't know how to prove that this task is NP-hard. And if we still want to get some evidence for the hardness of the problem, we need to assume stronger assumptions, namely the unique games conjecture that we shortly define. Good, so let's define what is a unique game. So a unique game instance is composed of a set of variables x and a set of equations x, where each equation is of a very special form, namely xi minus xj equal to b. And arithmetic is done over a field of size q for some, say, prime q. So what is one particular special case of a unique game instance? This is exactly the max cut problem. So how do you formulate max cut as a unique game? Well, for each vertex, you simply introduce a variable whose value is 0 or 1 to determine if we want to put the vertex on the left side of the cut or the right side of the cut. And then the fact that we want edges to be crossed by the cut just can be formulated as saying that xu minus xv is equal to 1 modulo 2 for every edge uv. Good, so an assignment to a unique game is simply a labeling of the variables by 0, 1 to the q minus 1, and we say an assignment satisfies an equation if it satisfies it, right? Good. So what is the goal in unique games? The goal is to find a good assignment. So we want to find an assignment that satisfies as many of the equations as possible. And the fraction of the equations that are satisfied by the best assignment is defined to be the value of the game. Good, so now that we know what unique games are, we can state the unique games conjecture. So this is a conjecture made by Subhash Kot in 2002, and it asserts the following statement. For every epsilon greater than 0, there is some alphabet size q, such that if I give you a unique games instance over alphabet size q, it's NP-hard for you to tell me if the instance is almost fully satisfiable or at most epsilon satisfiable. Okay, so this seems like a nice question, right? Because it's natural. It's studying linear equations over two variables and how hard they are to solve. So it's a natural thing to ask, but the main reason people are interested in this conjecture is because if you're willing to assume it, it gives you a very unified and complete view of approximation problems. So if you're assuming the unique games conjecture, you get optimal hardness results for many, many problems. You get a better than what we know for NP-hardness for other problems. And for some classes of problems, such as CSPs, you can even say what is the best algorithm for them. So this is a result of Raghavendra. So certainly there is a lot of motivation into studying this conjecture. But unfortunately, it's still a conjecture. We don't know how to prove it. So we try to convince ourselves, at least in one direction, hopefully not in both, whether we want to believe it or not. So what sort of evidence do we have for it? For the conjecture, we have some partial results, meaning if you change this 1 minus epsilon and epsilon to different things, you get to say that this problem is hard, but it's fairly limited. And we also have a kinetic construction by Kot and Moskovich of a hard Unigames instance. But it's a bit of a problematic candidate construction because it has two main drawbacks. So first of all, the word candidate means that they do not know how to analyze, and more specifically, they don't know how to show that the construction is sound. And secondly, even if it is sound, it is only one step, and it is also not polytime reduction. It is a sub-exponential time reduction. So even if it works, it will only roll out quasi-polynomial time algorithm, which is nice, but still it will not prove the conjecture. And against the conjecture, we have a bunch of algorithms. For now, I want only to mention one of them. So this is the algorithm of Aurora, Barak, and Stower. And what this algorithm does is it solves Unigames on surprisingly quick time. So obviously not a polytime algorithm, because otherwise it will not be a conjecture. What this algorithm does is it solves Unigames in time 2 to the n to the delta, where delta is small. It has some relation with this epsilon and with other things. But still it gets surprisingly fast time. Good. So from the title of this talk, you didn't see the word Unigames because I'm not going to really talk about Unigames. Instead, I'm going to talk about what is called 2 to 2 games, which is a closed problem. And the definition is almost the same. Again, you have variables, and again, you have equations, but this time, equations are of a more relaxed form. You require that the difference between xi and xj is equal to sum b or to sum b prime. So you have a wider array of constraints that you can use. So this problem is harder. And for this problem, Kot also made a conjecture in the same paper. And he conjectured that for every epsilon greater than 0, there is this alphabet size such that if I give you a 2 to 2 game instance, it's NPR to tell whether it's fully satisfiable or at most epsilon satisfiable. And the main result that I want to talk about in this talk is almost a proof of this conjecture, except for one small thing. So this is the following theorem. For every epsilon greater than 0, there is some alphabet size such that if I give you a 2 to 2 game instance, it's NPR to tell whether it's almost fully satisfiable or at most epsilon satisfiable. So up to this minus epsilon in the completeness, this is the same as the conjecture, but still it's not conjecture itself. And one nice thing that you can quickly see is that this gives you a new hardness cap for Unigames that subsumes all previous results. So you can show, and actually we'll do it on this slide, that this theorem implies that Unigames between half and epsilon is NP-hard. And the reduction is one line. So how do you reduce this equation into unique equations? You split it into 2, right? You break down these equations into 2. So if this equation was satisfied, exactly one of these will be satisfied, and otherwise none. So this is why you lose this factor of 2. So you get half minus epsilon, but then you can add epsilon trivial things just to have epsilon just on one side. Yeah. Good. So as I'll shortly argue this, you can view this as evidence towards the Unigames conjecture on a very surface level, because this is yet another new gap which at least guessed one of the endpoints right. The soundness is vanishing. But actually there is a bit of a deeper reason that I'm saying that. But before I say that, let me tell you some new NP-Hardness results that follow from this theorem. So obviously we have the two results that I already mentioned. We have some hardness for combinatorial optimization problems. Don't worry too much about these numbers, but we have some new hardness gaps for click, a variant of the coloring problem, and some gap for max cut. And finally, we have this intermediate CSP conjecture of Boas-Barak. I'll not say it is a conjecture because it's already proven. So it says that assuming the exponential time hypothesis, if you look at the problem, you need gains between half and 0.01 and ask, what time do you need to solve it? Then the time is of a weird form. It's not 2 to the n, it's not polynomial, it's somewhere in between. The complexity is between 2 to the n to the beta and 2 to the n to the alpha for some alpha less than beta. Good. And here is a sort of an open challenge to base more NP-Hardness results on the 2-to-2 games conjecture. And this is some result that we got. We didn't try too hard. And in fact, I'll say it in a few slides, but in the afternoon session, you will hear some progress in this direction by Ami Bangale and Subhash Kot. So let me discuss the history of unique games a little bit. So the history of unique games is sort of an ongoing battle between algorithm designers and reduction people and people that try to prove hardness. And the first algorithms that came out for unique games is actually by Subhash in his paper. So he showed some SDP formulation of unique games and was able to analyze it. He got something. And this SDP algorithm was analyzed better and with some variations by several authors with improved parameters. But obviously, no one refuted the conjecture yet. And then it was a question of whether the analysis is tight or some algorithm is needed. And it turns out that the analysis is sort of tight in the sense that this SDP algorithm cannot work simply because there is an integrality gap. You can construct an explicit graph on which this algorithm fails. This is a work of Kot and Vishnoi. So now it's back to the algorithms people to come up with a proposal for an algorithm. And they say the following interesting thing. Well, they observe that if your graph is an expander, then unique games is actually easy. And this is very interesting because if you take a random unique games instance, it will be an expander because a random graph is an expander. So this raises the question of how do you even expect hard instances to look like? Well, so we have some answer to that in the sense that there are partial gaps of hardness for unique games by O'Donnell and Wright and canonical construction of Kot and Moskovich. And then we have this sub-exponential time algorithm of Barak and Stower and some generalization of it by Stower that I already mentioned. And the point that I'd like to say is that the current result that says that unique games within half and little o 1 is hard says that also this algorithm will not work. So what do I mean? So you could have hoped that maybe this algorithm actually runs better than what it was shown to. Maybe the analysis could be improved. But the result here says that no, it cannot be improved for the following reason. So it turns out that if you look at this algorithm and try to run it on unique games instances with value close to 1 or with value half, it performs equally well. But now we know that one of these tasks is hard. When you run it on instances with half, it cannot succeed, unless of course p is equal to np. So this means that in general this algorithm is taking more than poly time. So again, you have no candidate algorithms that we need to try for unique games. So you can either view this as strong evidence for the unique games conjecture, or at the very least, if you still want to attack it algorithmically, you need to come up with new ideas, because clearly the current ones that we have do not work. So good. So because we started off with the click problem, let me just highlight this result. So this result says that, roughly speaking, assuming that your graph has a click of size 29%, now we can prove to you that it's NPR to find a click of size epsilon n. So of course it would be lovely to improve this promise, and the only way we know how to do that is by assuming unique games, but it would be very nice if there would be some other way to prove such results.
Yeah. So your reduction showed that unique games result for half. So you construct some graph which is stuff not in the smart.
Yeah.
So do you know what distinguishes it from the smart? Do you know spectral property?
So it's hard to say, because these instances usually come up as a composition of some base graph and some outer graph. So the base graph we understand very well, but the outer graph is like a mess. It comes up from some NP-Hard problem. So
distinguishes it from the smart. Besides the fact that
it's a good question. I'm not sure. So you also get some integrality gaps for the problem, where we start with random linear equation system. Then maybe you can actually analyze how the instance looks like spectrally. But I haven't done it. But it's a good question. Yeah. So finally, I'd like to mention this work of Bangale and Kot that you will hear about in the afternoon session. That sort of tells you that gives more progress in this direction. And roughly speaking, it gives you a generic way of transforming any unique games hardness result into NP-hardness result, again, based on this result, only losing a factor of 2. This is really generic, and it works for many problems. Good. So I'm going to talk about a little bit of what goes into the proof of the main theorem. If there are any questions about this part, this is a good place.
Any questions? What's the base level? Is it 0.29 versus epsilon? Using also half versus epsilon?
Yeah, so I believe half versus epsilon.
It's more than half and it's easy.
Yeah, so it's if you have a click of size. Yeah. So the question is, so Shaka asked me, what do you believe about hardness of click? Like for this problem, can we increase this 29% to 50%? So I said that yes, I believe that it should. This is the truth, and the reason 50% is like the sweet spot is because if you have 51%, say, then you can use some very simple ideas to show you can find a click of size 2%. Like independent set, 2 approximation vertex cover, and all of this stuff.
If you know you have got 90% and 90%,
that's probably difficult. 20%
Yeah, so right, when you have, so if you add this 50% result, you can just add some bunch of vertices and connect them to all and get something over 50%, but it will not be versus epsilon, but versus something else. So I'm not sure what you get, but maybe this is what you would get. Good. Good. So I'll not tell you the reduction in full. Instead, I want to focus on kind of one component of it, which is called the inner PCP. And this is a really simple object. It's a coding theoretic object. And what we need is the following. So we need an error correcting code C, as well as a local randomized tester T for the code. And two properties that we need is completeness and soundness for the test. So by completeness, we mean that if the test is ran on any legal code word, then it accepts with probability 1. And the soundness says that if I run this test on any word and I get acceptance probability bounded away from 0, say at least some delta, then this can happen only because W is close to some legal code word in C. And this is sometimes referred to as the local to global phenomenon because you have local information. You know that some local test accepts your word, and you are able to deduce closeness globally to some code word. So let me just put it out of the way. These are two properties that I needed. They are by no means enough. But still, let's run with it. So what do we mean by close? So usually we just measure the Hamming distance between W and C, and we want it to be bounded away for 1. We want it to be at most 1 minus epsilon. So in other words, we want W and C to be somewhat correlated. And this is called sometimes locally decodable codes or least decodable codes, and there are many examples. So close is a very loose sense of close. You want it to be correlated with C. Okay? Right, so this says this is the relative Hamming weight. So this says that W and C agree on at least epsilon of the coordinates. Yeah, this is at most 1 minus epsilon. Yeah. Good. So let's see one example, the most famous example probably. This is the Blue-Bloomby-Rubenfeld linearity test. So the code is simply the collection of all truth tables of all linear functions from 0, 1 to the n to 0, 1. Good. So what is the tester? Well, how do you check that a function is linear? You look at the definition and you do what it tells you. So you sample 2 points x and y uniformly from the cube, and you check whether f of x plus f of y is equal to f of x plus y, where all the arithmetic is done over f2. So clearly this test has completeness because if your function is linear, it always satisfies this relation. So the test passes with probability 1. And what you can show is that if the tester passes with probability half plus delta on some f, then this delta is correlated with a linear function. So in general, if you want to prove hardness for a problem A, the test T should say something about that. It should use checks of the form A. So for example, if you look at this BLR test from the right direction, what it really is a linear equation with 3 variables. The 3 variables being f of x, f of y, and f of x plus y. And indeed, you can use that to prove hardness for the Freeline problem. This was done by Hastad. And for us, we'll need a 2-to-2 test and an appropriate code. And this is what we present next. And let me just say that, again, our code will be encodings of linear functions. Not by truth tables, but by something slightly more complex. So good, so let me define the main object that will help us towards this goal. This is the Grassmann graph. So let V be a linear space over F2. Let K be its dimension, and let L be significantly smaller than K. So the vertices of the Grassmann graph are all L-dimensional subspaces of V. And two vertices are connected by an edge if they intersect in dimension L-1. So now we'll use this graph to define the Grassmann code, the Grassmann test, and then we'll discuss expansion on this graph and see how it all relates. So good, so we have the vertices and the edges up in the top. So let's define the code. So as I already said, the object that we want to encode is linear functions from V to F2. And we do that in the following way. To every vertex of the Grassmann graph, we associate a symbol. And that symbol is simply the restriction of the function little f to the subspace given by the vertex. So let's say it again. For every vertex, we look at the restriction of little f to that vertex. We write down some encoding of that linear function. We take all of these symbols, and this is our encoding of f. So just to see that we're on the same page, let's check some basic properties of this code. So first off, note that the alphabet size of this code is 2 to the L. And why is that? Well, the symbols are linear functions over subspaces of dimension L. And because we're over F2, there are 2 to the L linear functions over L-dimensional space. So this is why the alphabet size is 2 to the L. And it's very easy to see that the length of the code is the number of L-dimensional subspaces that V has, which is roughly this number. So lastly, let's say what the distance of the code is. So let's take any two distinct linear functions. What is the fraction of subspaces in which they agree? Well, on any given point, they agree with probability half, right? Because two linear functions agree on half of the places and disagree on the other half. So if you take a random L-dimensional space, which roughly corresponds to taking L-independent vectors and taking the span, the probability that F1 and F2 agree on the subspace is half to the L, or 2 to the minus L. Hence, the distance is 1 minus that. Good. So now we know what the code is, and next we present the test. And the test comes from the edges very naturally. So what you do is you sample an edge, L, L prime, uniformly at random. You read off the symbols on L and L prime, and check these two functions agree on the intersection between L and L prime. So let's see this test is of any relevance to us, meaning that this test is a 2-to-2 test. And indeed, let's fix any L and L prime and fix a function on the intersection between L and L prime. So how many linear extensions does it have to L? Well, you have one extra dimension, and you're over F2. So you have two extensions. And similarly, you have two extensions to L prime. And this is precisely the reason this test is a 2-to-2 test. Good, so this test is of some relevance to us. So next we can check whether it satisfies the completeness and the soundness. So completeness is one line, right? So if you have a legal code word G, then of course it passes the test with probability 1, because these two functions are restrictions of the same function. So of course they are consistent. And the really interesting question here is about the soundness of the test. And so is the test sound? So the short answer is no. You can actually show some functions that are far from all legal code words, yet pass the test with significant probability. But you can consider more complex notions of soundness, which are actually true and are useful. But I don't want to spell it out. So let's recap what we've seen so far. So we discussed hardness for 2D games and some of its corollaries. We presented the Grassmann test. And we concluded that the interesting question that we need to ask ourselves is what sort of soundness you can prove for this test. And next up, I'll try to tell you that studying properties of this test really corresponds to studying edge expansion properties of the graph, which is a much simpler notion because it's only combinatorial. You don't care about any assignments, any test. You only care about vertices and edges. So let's see this relation. But before that, let me pause for questions if there are any. Good. So let's talk about expansion. So what is graph expansion? So let G be a D-regular graph, and let S be a set of vertices. The expansion of the set S is the escape probability from the set S. More precisely, you sample a vertex from S, and then you take a random step from it. What is the probability you land outside S? What is the probability to escape S in one step? And just to give you some context, usually we say a graph is an expander if the expansion of any set of size at most 50% of the vertices is bounded away from 0. But for us, the notion that we consider is the notion of small set expansion. So we want a stronger guarantee. We want the expansion of any small set to be, so it's not stronger, it's a variant. We only care about small sets, but for them we ask for more. We ask that the expansion is close to 1. So this is the notion of small set expansion. So is the Grassmann graph a small set expander? And secondly, why do we care about this question? How is it related to the test that we just discussed? So here is a nice connection. You can actually show that the soundness of the test is equivalent to the fact of whether the Grassmann graph is a small set expander or not. And I'll only show you one direction, but I think that it gives a very nice intuition into this connection. So let's suppose that the Grassmann graph is not a small set expander. And using that, we'll construct a function that passes the test with constant probability, yet it is far from any legal code word. So indeed, let S be a small set with expansion bounded away from 1. So what we want to do is take this set and use it to construct many sets that have small expansion so that we cover a sizable fraction of the vertices. And indeed, it's a nice exercise. You can show that taking the set S and applying random linear transformations to it, plus some massaging, you can get a collection of disjoint sets S1 to Sm with the following two properties. So first of all, each one of them is small individually, but together they cover constant fraction of the vertices. Secondly, the expansion of each one of them individually is at most 1 minus epsilon for some constant epsilon. And given these sets S1 to Sm, we can actually construct an example where the test fails. And here is the example. So let's draw our sets S1 to Sm. And the example goes as follows. So for each set Si, we'll pick a linear function hi for it randomly. And the assignment simply says the following thing. You look at the vertex L. If it is inside Si, you assign it according to hi of L, restricted to L. And if L is not inside any of this S1 to Sm, you assign it randomly. Or even you can think that it doesn't exist. So we need to notice two facts. First of all, if you run the test on this assignment, it passes with noticeable probability, with constant probability. And why is that? Well, because the sets S1 to Sm cover a constant fraction of the vertices, they also cover constant fraction of the edges. But we also know that for each set Si, if you take a random step from it, you stay inside the set Si with constant probability. And if you combine these two facts, you get that constant fraction of the edges go from one Si to the same Si. And now all that you need to do is to observe that all of these edges are satisfied, because it's the same function again. However, you have no global structure. You are not close to any legal code word, and this is because each one of these sets is small. So none of this H1 to Hm is really a candidate, and other functions simply have no chance. So this is a very nice connection that shows that if you are not a small set expander, if the Grassmann graph is not a small set expander, then the test is not sound. So what can we say about small set expansion? And the short answer is that the Grassmann graph is not a small set expander. There are small sets with expansions bounded away from 1. So you have to consider different notions of soundness. And actually, we have examples of such sets of two types. I'll not say what they are. And if you run this construction, you get a set of counterexamples for the test. And we're very optimistic about it. We thought that maybe these are the only examples, at least morally speaking. And we were able to prove the following statement. If there are no other counterexamples to the test, then you do get the 2-to-2 games conjecture. So I'm hiding a lot of things here, but sort of this is the best thing you can hope for, at least in the current picture. So from the previous slide, at the very least, we need to understand what are all of the sets, the small sets that have expansion bounded away from 1. And this is the question that we raised in this paper with Dinur, Kindler, Kot, and Safra. And we also proved some partial results. And following our work, Barak, Konthari, and Stower showed that, in fact, studying this expansion question is enough. It's a very nice and short argument showing a reduction in the other way. So now we come sort of to the end of this effort. So together with Kot and Safra, we actually got the complete characterization of the non-expanding sets that was needed to complete the proof. Hence, we concluded the theorem.
any characterization.
You need it very specific. Like, as I said, there are two types of examples here. You can sort of combine them, and the sort of characterization is that this is basically the whole thing. Yeah. Good. So we have these two important notions that we discussed so far, the soundness of the test and whether the underlying graph is a small set expander. And we saw a relation between them. And for those of you that are familiar with analysis of Boolean functions, you might have heard about this thing called the hypercontractive inequality. It sounds scary, but it's really simple. We'll shortly see it. And you know that small set expansion and hypercontractivity is really linked together. It's basically the same thing, but really this is stronger. But in our case, actually, the graph was not a small set expander, but still we were able to characterize all sets that violate it. And then we got some non-traditional notion of soundness that I didn't discuss, which was good enough. And this raises the question of, can we complete this picture? Do we have, again, a link to a variant of the hypercontractive inequality? So does this error exist? Good. So what I'm going to say now can be said about many settings, including the Gassman graph, the Johnson graph, the symmetric group, but I'll be focusing on the biased Boolean hypercube, which is sort of the most basic variant you can consider. So what is hypercontractivity on the uniform hypercube? So here's a quick definition. Let x be a Boolean vector. The distribution y over row correlated inputs with x is defined in the following way. For each I independently, you pick yi to be equal to xi with probability rho, and otherwise you resample it. You take it to be a uniform bit from 0, 1. So now that we have this notion of correlated inputs, we can define an averaging action on functions according to this distribution. And this is the T-row operator, defined as follows. So T-row of f is a function, and the value of this function on input x is the average of fy over y's that are row correlated with x. So you can think about it as you take an input, you sort of draw a ball around it with sort of this radius, and you take the average of the function over that. Except that it's not really a ball, it's something more smooth. So you can easily show that since this T-row is an averaging operator, and the distribution of y and x is the same marginally, then T-row is a contraction. It can only decrease LR norms. And when we say something is hypercontractive, we mean that something actually stronger happens. And this is a theorem of Ponami, Gross, and Beckner. So it says that T-row is actually a contraction from LR to LQ for some R larger than Q. In notation, the R norm of T-row of F is smaller than the Q norm of F. And there is some precise relation between R, Q, and rho that I don't want to get into. So I'll just state the most canonical setting. This is called 4-2 hypercontractivity. It says that the 4 norm of T-row of F is at most the 2 norm of F for some rho constant greater than 0. And as I've suggested already, this is really a key tool. It has a ton of applications throughout math and also in TCS. Here are a few of them. So we have the well-known KKL theorem, we have sharp thresholds. You can prove that the noisy hypercube is a small set expander using this inequality, and a bunch of more results. There are far more, and even each one of these bullets has lots of sub-bullets, but really these are some of my favorites. Yeah, so this inequality is really cool. I just want to quickly show you how it implies that the noisy hypercube is a small set expander. It's very simple. So let's recall the hypercontractivity inequality again. And what we'll show is that this correlated input graph is a small set expander. So this is yet another connection in this diagram. It shows that hypercontractivity implies small set expansion. So let S be a small set, denote its fractional size by delta, and let's consider the indicator function of S. So we want to show that the probability to escape it is at least 1 minus some function of delta. So instead, we'll show that the probability to stay inside it is smaller. Yeah. So what is the probability to stay in it? Well, it's the probability to pick X in the set, pick a row correlated input, and stay inside a set. And now we want to massage this into some linear algebra expression because you want to use norms and things like that. So first of all, you remove the conditioning that X is inside S. And you can do that if you multiply by 1 over the probability that X is inside S, which is 1 over delta. And then you observe that as usually happens in spectral graph theory, these sort of probabilities can be written as inner products of the indicator vector of the set times T row of the indicator vector. And then you can show that this is at most delta to the quarter. And here we use hypercontractivity. So namely, first, by Holder. So you want to reduce 4 norms of T row of F. So it makes sense to use Holder inequality with norms 4 over 3 and 4. And then you just use hypercontractivity and compute the 4 over 3 norm and the 2 norm of the indicator function, and it works out. I don't want to spend too much time on it, but this is really a short and neat proof that shows that hypercontractivity implies small set expansion.
Complete graph, points on edges.
Yeah, it's a way to do it. Good. So if I had more time, I could explain to you like what this means intuitively about sort of the Fourier spectrum of the indicator function, because here you can actually see what happens in KKL and all of that, but maybe some other time. So instead, let's spend the last 5 minutes on discussing what can you say about different domains. So the first question is, does hypercontractivity hold? And again, as I said, the domain that we consider is the bias cube. Again, the vertices are 0, 1 to the n, but now we consider them with a non-uniform measure. We consider them with the mu p measure, where p is little of 1, say 1 over root n. And you have the same definition of correlated inputs. You keep the bit with probability rho, and otherwise resample it according to the correct marginal. So does hypercontractivity hold? And the short answer is again no. And the example is very simple. You just take dictatorship. So you can show that for constant rows, the 4 norm of T row of F is roughly 4 to the 1 over p to the 1 over 4, whereas the 2 norm of F is p to the half. And when p is small, this is much larger than this. So it breaks. So do we give up, or do we do something else. So the way we overcome this barrier is we simply state a different statement that for such functions is useless or trivial or is not helpful. But for other functions, it is very meaningful. And the idea here is to note that this function is very local, meaning very small coalitions, only one variable, affect the output significantly. So what we want to do is to state a statement that works for non-local functions. And let me just say that if you're really interested in the counterexamples to the SSE of a Grassmann graph, one of them really draws intuition from this example, although actually we saw this relation only after the whole thing went through, but never mind. Yeah, so I'm not going to give the precise statement. I'll just say roughly what it is. This is a joint work with Kiva, Schlong, and Lifshitz, where we show hypercontractive-like inequality for global functions, where again, global means that no small coalitions have large influence. So this is a fairly new tool, but already we have some applications for it. So we have some application for sharp thresholds. So we can show the invariance principle. We have some application to extreme combinatorics, noise sensitivity on the p by s cube, and more. But this is really only a partial picture. There are more results, and actually we can prove such statements not only for the p by s cube, but for a much richer class of domains, such as product domains, but actually a little beyond that even. So let me summarize the talk. So we touched on kind of two topics. We discussed PCPs, namely the 2-to-2 games conjecture and some of its corollaries. We discussed small cell expansion, new notions of hypercontractivity for the Grassmann graph, phi by s cube, and so on. And what about the future? Well, I'm really positive that these new tools and techniques will find some new applications, and who knows, maybe we can make even further progress towards the games conjecture, even though, yeah, so that's all I wanted to say. Thank you.
Question?
So if you wanted to improve this hack to something better, so if you have the best approach to it.
I can tell you about, so Shachar asked what is the best approach, in my opinion, to improve this half to something better. And the sad answer is that I don't know. So I tried some things. So for example, you can try to, so this half is actually the second eigenvalue. So it's also it's the second eigenvalue of the Grassmann graph. But this is not really the point, but it's like the smallest field you can have is F2. So this is like one over the smallest field. But still you can try to find maybe interesting graphs. Like Grassmann graph has a lot of eigenvalues close to 1, where close is half. So I try to think about graphs that have even closer to 1 eigenvalue that I don't know anything like that. I'm not sure if it exists. So like it would be a good question or good challenge to ask if there are any such graphs. I don't know. Maybe you can try to start from this result and do see some parameter that's improved from what we had so far, and like get smoother, better smoothness parameters for the PCP, which is something that again I didn't define, but yeah. So in short, I tried stuff, it didn't work.
So what's the trade-off between soundness and the alphabet size? Explicit.
Yeah, so it's explicit. I don't remember it, but it's close to optimal.
So it's polynomial in the alphabet size.
Maybe a bit worse, but.
Quick question about the connection between hypercontractivity and responsive expansion.
Mhm.
So basically, I mean, you're working with vector and studied cyclocontractive properties and showed that if it does not expand, then there is a small collision that affects it. That's the...
Yeah, and roughly speaking, what you do is, if it's not hypercontractive, it means that it has low weight on some low, it has high weight on some low level. No? And what you show then is that once you have high weight, you can actually get sort of large Fourier coefficient. Not really large Fourier coefficient, but morally speaking, this is what you get.
And that's the characterization you were looking for?
Yeah. So you want to be able to go from being small set to being large by only restricting a few variables.